Sometimes it works.
PowerPoint and
yeah, I think the problem was just that I changed the display. So those of you who are doing check-in and check-out, or reading the check-in messages, will have seen that there was quite a bit of activity with the so-called test field module. And because I was so much involved in this, I want to tell you a little bit about why this was such an important thing, and it still is a very important thing. The test field module actually started with the SVN revision number 4200, and now we have 10,000. So it actually started halfway through regarding revisions, but that really corresponds, it corresponds to the year 2004, 2005. So it is approximately halfway into our pencil code time. But it really only was in the last few years that this whole thing took off. So here is the scientific output so far using the test field method. It started with one early paper in 2005, and then there was quiescence, and then it really started with a bunch of papers all of 2008 here. So it started off with the paper actually with Axel2. When he came, he is from some place in India, but working with Kanaswami Subramania at Pune University, and he was visiting us at Nodida, and they were asking whether it is really true, whether the kinematic alpha effect and the kinematic diffusivity are strongly dependent on the magnetic Reynolds number, as they are in particular flows, like, for example, the so-called Galloway-Proctor flow. But we wanted to answer this question for isotopic homogeneous turbulence, and that's what we did. And the most exact method, most accurate method for doing this is by using the test field method, which I will explain in a moment. The other, so this is for isotropic turbulence, kinematic alpha effect in isotropic turbulence simulations. We also had a paper with Petri, who is here, where we calculated the magnetic diffusivity tensor, magnetic diffusivity tensor. So these are not necessarily always isotropic objects, they could be tensors, and that's also what we can calculate with this method, in the case where we have rotation and we have shear turbulence. So it's, of course, rotation introduces anisotropy into the turbulence, and shear also does the same thing. And then we had another paper where I forgot to include any transparencies into this talk here, the so-called scale dependence of the diffusion and also the alpha tensors. If you look at diffusion properties of a large-scale signal, the amount of diffusion may actually depend on the wave number of that signal that you have. And that's what is meant by scale dependence. And that really corresponds to saying, so in other words, if you take the diffusivity at a certain wave number, then you have a corresponding viscosity or diffusion coefficient that depends on the wave number. And it's in limited cases when the turbulence is small enough of scale that this doesn't really matter. But once the scales of the turbulence becomes comparable to the scale of the signal that you are looking at or that you want to diffuse, then it becomes important.
So does the diffusivity fall normally?
It falls, yes. Normally it falls. For turbulence it falls.
Because the larger scales are just large scale erection and are not really diffusing. The larger scales, they're just kind of...
It's, no, I would simply say it becomes less efficient if the two scales become comparable. And it behaves in wave number space like a Lorentzian. That means 1 over 1 plus k squared. Or k divided by kf squared. So yes, and then we did the same thing for accretion disk turbulence. That's in this paper included. And then we, for the first time, did the same thing for the nonlinear case. That's in this paper. So these last three papers are still in submitted modus, but they're all on the archive here. And so this one is the same thing as basically the Axel2 paper, but then now for the nonlinear case. This is a case here where Druber, Mitra, and Petri Kepler and Lisa Tabakol have been collaborating with me, and this is where we look at the alpha effect density visibility. So in that sense, like this, but in the presence of shear. So then there's also anisotropy. And then finally, another paper which actually is not using the test field method as such, but it uses the test field module, because the equation is very similar to the induction equation, and we wanted really to use the induction equation in parallel to the rest of the MHD equations, and that's done in the paper here with Zügner and myself. So why do we look at alpha effects and turbulent diffusion? The reason is really that in many situations in astrophysics we know that large-scale magnetic fields can be generated. We want to understand why this is the case. In astrophysics, of course, we know the Sun has a large-scale magnetic field, galaxies have a large-scale magnetic field, and we need to pin down at some point or the other what are the precise mechanisms that actually do accomplish this. But examples of large-scale field generation in numerical simulations are manifold. Here's one of just helical turbulence. Everything completely isotropic. There's no shear or no rotation. Just helical turbulence. Helical turbulence is isotropic and homogeneous. People often say, if it's helical, how can it then be isotropic? Yeah, that's really because helicity does not violate isotropy. Helicity, you should think of a box of screws. So each screw is right-handed, right? In that sense, the whole system is right-handed. But if the box of screws is mixed, you shake it, then all the screws are completely randomly oriented. So all directions are represented. And yet it's fully helical, or could be fully helical.
Oh, what? Sorry?
Screws. A screw.
Oh, okay.
Or spirals or something. You take lots of spirals in a box, so they all point in different directions, but they all have the same handedness. That's what this is, of course, about, and other people in biology would call it, of course, chirality. But that's not really, there's no direct connection with magnetic fields here, we think. So what you see here is that what is shown is cross-sections of a component of the magnetic field at the periphery of one side of the box. And you see it at different times. During the early phases, when the magnetic field is still growing, it's randomly oriented, and only at later times the magnetic field builds up a really large-scale structure here. Another example here is a simulation from Petri, where there is also shear flow present. In that case, time is shown along this axis, and one spatial coordinate is shown in this direction. And that's the direction which is perpendicular to the plane of the shear flow. So what you see is both the x component and the y component both are, this is the streamwise component, this is the cross-stream component. In both cases you see after some time the buildup of a large-scale magnetic field. Large scale means if you average the field, averaging is indicated by an overbar, you get something which is finite and of significant amplitude. And in this case, there is a finite amplitude magnetic field, and it also shows long-term spatial and temporal order. Spatial order because if you look at this as a function of space, you see a sinusoidal modulation. If it as a function of time, you also see a sinusoidal modulation. So it's large-scale spatial temporal order. And this, of course, is basically what is going on in the Sun, for perhaps similar reasons. We don't know yet. Another example of large-scale magnetic field generation are these following two examples, which are different in the sense that in those cases here the turbulence was driven by a random body force in the momentum equation. And that's something which is really artificial. There's hardly any force in nature which really acts as a full body force. The closest we could have is if you have supernova explosions in the galaxy. That could act as a body force to a reasonable approximation. But otherwise, that's really not the case. And instead, the source of instability is not an explicit driving, but it is an intrinsic instability in the fluid. And there are two types of intrinsic instabilities. One is the convective instability, and the other one is the magnetorotational instability. The convective instability you have if you have heating from below, and you exceed a certain critical radial number, you find convection, and so this system here, it's again a simulation by Petri, is showing convective turbulence throughout this entire time. And at a certain, during this time, magnetic field is exponentially growing until it eventually reaches equipartition. That means that the magnetic energy becomes comparable to the kinetic energy. And when this happens, in this case where he has sufficiently strong shear, in other cases where there's also such shear, that would not happen. So what happens in the presence of shear is that he actually generates also a large-scale magnetic field with a certain spatial modulation, and in this case a temporal order which is constant in time.
In this setup, in this run, you have no shear until 400, and then...
No, there's shear all the time.
All the time?
All the time, yes. And what we see is that the prominent large-scale magnetic field only shows up in the saturated state. And that's very typical. We had the same thing in all the other cases so far. So far, we don't know really of large-scale magnetic field generation in the kinematic regime. But that's all.
Yeah, sure, but
in
that case, it's so average.
It's exponentially growing, so you just don't see the...
You also don't see it very much, yeah.
field.
Yeah.
Yes, so it's so average, then, okay.
You're wondering whether there is maybe a large-scale field, but you don't see it because it's so weak. Is that what you're saying?
Yes, but what he's saying is you have to know, I agree that you have no large-scale field knowing linear growing, but and then, okay, just in one time, boom, you get the large-scale field.
But that's the same case in the second plot on the right.
Right, it's the same.
Yes.
Yeah, but here the large-scale is growing progressively.
I would have almost had another plot which would show the ratio between the average component, which is the large-scale component, and the total field. And Petri may not have done so. So that those typically reach something like 50%, these ratios, after those times, and they're typically on the order of 7% at early times. And 7% is also what you would expect if you have a certain finite number of eddies in a simulation. Then you would get a random number, plus and minus. You will always get a finite average, just because you have, if you roll the dice 5 times, for example, you will never hit exactly the average. You will always have a Gaussian distribution around the average. Okay, and that Gaussian distribution has a certain width, and that's what generates these 5% or 7% in the early stage. So with magnetic nonlinear unity, we don't know of any example of a large-scale magnetic field in the kinematic regime. But in the nonlinear regime, we do have successful dynamo action in many cases. So these are then, and that's finally the example of the magnetic rotational instability. A number of you are interested in, especially Anders here. And there we have, again, spatial order, in the sense that there's a large-scale magnetic field here. Here it actually looks at certain times a bit anti-symmetric, but not quite. Here it's more symmetric again, with respect to the top and the bottom of the domain.
What is the boundary condition?
In this case, it's a potential field condition.
So we do with periodic boundaries. It is occurs even with periodic boundary conditions.
Yes, that really is, of course, rather remarkable.
Axel, one question. So
Yeah.
you see these large-scale field structures function of Z. But if you want to average over, say, in the other direction, and take it from the Y and from the X, would you see zero power? Or would some of the power on the Z-dependent mode somehow spill over to some modes that depend on X and Y also?
So you ask whether there's a dependence on X and Y?
Yes, just
Even
if it's 10 times smaller. But I'm asking, is it a million times smaller or is it 10 times smaller?
I mean, it's never that much smaller. It's normally 10% smaller. I mean, 10 times smaller. That's basically related to what I just said earlier, that if you have completely random conditions, you have 7% of the ratio of mean to average field, mean to total field. And if you have in a large-scale dynamo successful and fully saturated, then you have 50 to 70%.
Well, I'm not talking about random field, I'm talking about ordered field, but not only Z-dependent, but maybe X-dependent.
Yeah.
So
I mean, you yourself told me that you actually found some evidence for such.
yeah, but I'm just wondering if just the fact you have a very a strong large-scale set-dependent field, if just some nonlinear interactions there would mean that it spills over and creates a little bit of power on X-dependent modes also.
I mean, you would, if you have an interesting story to tell, then it would be one where it would not just be the spilling over, but there would be a real mode in X and X direction. And that's certainly a possibility. It's certainly a possibility. So if you find this, that's great, and it should be understood and modeled further. And the bigger the domain is in the horizontal direction, the higher chance you will have to find that. And once you find such a thing, one can and should look at such things again with the test field method, which I will mention in a moment. At the moment, I make a pre-selection. I basically ignore then by averaging over the X direction. I will ignore the X dependence and also the Y dependence. The Y dependence could be interesting. These are phenomena that in the sun are called active longitudes, for example. And some people see such things in rapidly rotating convection simulations. So, in other words, if you do a real simulation and you find structure in any direction, you should of course not choose averages that eliminate such a structure. So the averages should not be something magical, and you should not be looking what happened before you average. You should first look what happens, and then you will see some structure, and then you do the average, and the average makes the structure only more pronounced. And then you ask yourself the question, if given that there is such a large-scale structure, is there a way of understanding the origin of a large-scale structure in terms of a simpler theory? So if you have a structure which is really just depending on the z direction and on time, you may wonder whether there is a simple, reduced theory which only depends on z and t. One of the things, of course, I should remind you of, based on the original equations, such a thing can never work because a dynamo requires 3 dimensions. There's no dynamo which works in 2 or even 1 dimension or 0. So dynamos require 3 dimensions. There's no way of simplifying this. And if so, it would only be a description of what happens at large scales. And that's called metric theory. Yes, I thought of slipping in this one picture here because we have heard a little bit about turbulence simulations, about spectra. And that's how a compensated power spectrum looks like. Niels, of course, has been looking at compensated power spectra throughout most of his years around 2004. He has had 8 papers, all of which have compensated power spectra, I think, in one way or the other, most of them. And so this is the typical case of a magnetic Prandtl number of unity. A compensated power spectrum means, power spectrum means you are doing a Fourier transform, you are averaging over shells in wave number, and look just at the radial dependence in wave number space, and that's what's plotted here. If you have a Kolmogorov spectrum, the power would fall off like k to the minus 5/3. If you compensate by k to the plus 5/3, so that the result is flat. And so here you see that it's reasonably flat, and by having a normalization with respect also to the total dissipation by some factor, the whole result becomes non-dimensional, and this value gives you the so-called Kolmogorov constant, which is a little bit bigger than unity typically. But this is now for helical turbulence. That has not been done before. And this is Prandtl number 1 at 512 cubed resolution. What you see first of all is this is the injection scale of energy at this wave number 4. You see then a Kolmogorov cascade to the right, and then there is being energy dissipation at approximately this wave number. So that means all the energy is going down to smaller and smaller scales, and then it's being dissipated. But there's a small amount of energy which does not go to the right, but it goes to the left, and that's all the stuff that has to do with the knottedness of magnetic field. It's the fact that magnetic field is helical. And magnetic fields have the property of this knottedness being a conserved quantity. And so you cannot bring it to smaller and smaller scales, and your knots would be tighter and tighter, and that really is impossible. So the only way that they can go is to expand, to relax. That's how a knot can behave. So the only way for a knot to relax is to go to larger scale, and that's what happens here. So you hear the dark line is the magnetic energy, whereas the dashed line is the kinetic energy. Kinetic energy, of course, will go down because there's no supply of energy anymore, there's no inverse cascade of kinetic energy, so no kinetic energy at large scales, but in the magnetic energy, because of this conserved quality, being magnetic helicity, there is magnetic energy at large scales, and this is in the final saturated state. And now the interesting question is what happens at smaller and smaller Prandtl numbers. Of course, what you also have been looking at back then is this work which is papered together with Chekhov-Zhihin and Niels. These are lines of constant magnetic Prandtl number. If you go to smaller and smaller, this is for unit Prandtl number here. This is a Prandtl number of 0.1, and this would be 0.01, the diagonal lines. Then the critical magnetic resonance number that you need to reach before the dynamo becomes excited becomes bigger and bigger and bigger, making it eventually impossible to get your dynamo working.
Does the dynamo get equally excited? I mean, getting excited is just material to dynamo actually, but is it always the same